All right, hi everyone. So this is going to be an extra example of something that was briefly mentioned on our Monday class, and is also an example of something we talked about on Wednesday. So the problem that we're going to be looking at is the following. So we're going to find the Maclaurin series, meaning the power series centered at 0 for inverse tangent, and then we'll also find its interval of convergence. Okay, so a lot of the examples we had been seeing Monday and earlier looked like essentially geometric series. And this is certainly not looking geometric. But the fact that we can use is that inverse tangent is the integral of 1 over 1 plus x squared. And so what we are able to say is that a series for inverse tangent is going to be the integral of the series for 1 over 1 plus x squared. And that is looking geometric, so that's something that we're able to find. So first, let's find a series for this function, 1 over 1 plus x squared. We did do this in class, but as a reminder of how we did that, it needs to be 1 over 1 minus something. That something is negative x squared. And so we can say that the series is the sum from 0 to infinity of that thing being subtracted squared. So minus x squared all raised to the n. And then raising the factor separately to the nth power, we get that this is minus 1 to the n, x to the 2n, which if you like is 1 minus x squared plus x to the 4th minus x to the 6th, and so on. So only even powers, and they're alternating. So that means that inverse tangent is going to be the integral of this series. And what we're able to do is we can integrate this term by term, meaning we can actually think of each term has this expression, integrate all of them using the power rule separately. And then take the series of what the power rule gives you. So when we're integrating, I should write a little dx in here, x is the variable, so minus 1 to the n doesn't do anything. But x to the 2n, we increase that exponent by 1, we divide by that new exponent, and then we have this plus c because we integrated. So what this series looks like is we have our constant, and then starting at 0, goes in. If we put in 0, we have just 1, an exponent of 1, and a denominator of 1, so that's plus x. If we put in 1, that's minus x cubed over 3. If we put in 2, we're positive again, then x to the 5th over 5. And what we're seeing is exactly what would happen if you use the power rule on each of these terms separately. So this is our series. And what we know is that since the original series, this works as long as the absolute value of x is less than 1. Here, this series works also as long as the absolute value of x is less than 1. So there are two things that we need to decide. First, this is a c, but this is an actual function. So we want to think about what constant makes the series actually give us the inverse tangent. And we can do this by actually testing a point and seeing what happens. If we put in 0 to inverse tangent, we get 0. And if we put 0 into the series, all of these terms become 0. We get C. So in this case, it turns out that the C, there is no constant. The sequence is really x minus x cubed over 3, and so on. So we have that inverse tangent of x equals our series -1 to the n, x to the 2n plus 1 over 2n plus 1. As long as the absolute value of x is less than 1, we keep that same radius of convergence. But for the interval, the question is, what happens to the endpoint? So what happens at 1 and -1? If we put in x equals 1, one to any power is just 1. So we get this alternating series. And to skip some pretty standard type work, you can show this converges by the alternating series test. So you would actually show the Bn is 1 over n plus 1, or 1 over 2n plus 1, that decreases and goes to 0. So the alternating series test says it converges. If we put in -1, what happens is -1 to an odd power is -1, and it's always -1 because we're always raising it to an odd power. So that means we just have one single extra factor of an alternating series, or one extra factor of -1. So we still have an alternating series. So while the alternating happens in a different direction, so here n equals 1 makes it positive, here n equals 1 makes it negative, we still can use the same process. This converges by the alternating series test. So in this case, the interval of convergence, we had said from the radius gives us that we're between 1 and -1, but we check the endpoints, and those actually both are in the interval of convergence. A power series converges at 1 and -1. So the interval of convergence is the closed interval from 1 to -1 because we check the endpoints and those are in there. All right, so there'll be other examples in class, but this is one that briefly showed up in class on Monday, and here are a few more details.